Hi class. This is going to be an exam where I do I guess, voice walkthrough of taking an exam. Um, I just wanted to give you an idea of the thought process that you go through when you answer these questions. So the way that I would suggest doing this, I've provided you um, my exam that I gave last fall. Um, my exam 2 that I gave last fall to my normal class, not to my online class, but some of the questions are, I mean, all the questions are similar. You know, I mean, you guys cover the same content, so the questions are at least similar. Um, but this will just be another study tool for your upcoming exam 2. Basically, what I'm going to do today is I'm going to run through the key, read through each question, and tell you how I came about that answer. So just saying, like, you know, why did I do what I did? Oh, and my alarm is going off, which means that it's in the morning here. So anyways, sorry about that. So yeah, so the way that I would suggest doing this, you could go ahead and pause the video, print out the exam, maybe take the exam yourself, and then just see where you got stuck or whatever. So I guess I just wanted to give you, so you'll have the blank exam, you know, for this practice exam. You'll have the answer key that I'm looking at right now, that you're looking at right now. And then you could have this video as well, which is just me explaining essentially the answer key or explaining why I did what I did in that. I'm doing that because writing it out at this point, I think the video would take me an hour and a half. It's always a little bit harder to write with the stylus than it is just to obviously just talk through it and write with a pen and paper and whatnot. And this is already done, so I don't want to. I just didn't want to do it. And this you can play back and everything, so you can hear what I have to say over and over and over again. Okay. So let's get to it. So a lot of this junk you can ignore. So like the X's, the check marks, and all this stuff. When I make a key, it's after my first run through of creating the exam, so I make it my key when I answer the questions, and then I also do like my edits and revisions to the exam, so it's my second walkthrough. And then I tend to write stuff on there too. So there was a median score of this exam, and then an average score, and then apparently the number 85,529 for whatever reason. I don't recall. All right. Actually, I do think I remember what that was. I think that was, never mind. Okay. Anyways, so let's just look at this, and I'll just walk through, and I'll tell you why the answer is what it is to each one of these questions, okay? All right, number one in the seven-step hypothesis test process, that is used in this course, the fourth step is likely used to run any calculations in regards to your test statistic. That is patently false. You know, I mean, that's for sure false. The reason why that's false is one of two things. The fourth step is when we establish what the critical values are, or when we establish what our rejection regions are. There's no calculations in that step. That step contains us looking into a table to find our critical values and then ultimately write our rejection region. The fifth step is when we gather the data and we run a calculation using the formula that we have, or the testing statistic that we have. Okay. A random sample of number two. A random sample of 36 is taken from a population with mean 50 and standard deviation 5. What is mu sub x bar? So what is the mu of the sampling distribution? And this is just asking, do you understand the central limit theorem? Do you understand the idea of a sampling distribution? And if you do, which means you studied that portion, which I believe is module 6, you'd know that mu sub x bar, the mu of the sampling distribution, is just equal to the mu of the underlying distribution, right? So the mu, or the population mean, of the underlying distribution being 50 would just mean that, yes, the mu of the sampling distribution is also 50. 3. The width of a confidence interval will be either A, narrower for a 99% confidence interval than for a 95% confidence interval, wider for a sample size of 100 than for a sample size of 50, narrower for a 90% confidence interval than for a 95% confidence interval, wider when the sample standard deviation is small than when it is large. Alright, so why is it not A? Narrower for a 99% confidence interval than a 95% confidence interval. It's not going to be A because we know that it's going to be wider. Why do we know that it's going to be wider? We know that it's going to be wider because when you use a 99% confidence interval, regardless of whether you're using a T distribution or a Z distribution, what ends up happening is the critical value that you're using is larger. Alright, so picture that formula that when you can go and look at your chart here. So you'll have a chart for this exam. So if you look at your chart, kind of crane your neck here to look at one of these confidence interval charts, the X bar. Maybe I can do this. Hey, there we go. The X bar plus or minus Z alpha half divided by sigma over square root of n, X bar plus or minus T alpha half, whatever one that is. When you get when you're looking for a 99% confidence interval, you're going to be using a larger Z alpha half, which is then going to expand that range. Okay, let's do this again. All right, that worked out. Wider for a sample size of 100 than for a sample size of 50. Let's see, we can look at our formula again. Is it going to be wider when the sample size gets larger? No, it's going to be skinnier. Because if you take a larger version of n, it is going in the denominator of either one of those formulas, and it's ultimately going to make that margin of error piece smaller. So then that's going to skinny up the interval. Sorry for the sniffles, guys. We're getting over about a month long of having a virus and cold and flu in the house. Literally a month long. Yeah, we're 5 days away from it being a month. No fun. Okay, and C, narrower for, well, let's do D first because we know that D is wrong. Wider when the sample standard deviation S is small than when it is large. So these are all similar concepts. We're just looking at this formula. So when sample standard deviation S is small, is that going to be wider or larger? Well, when it's small, it's going to make this margin of error piece smaller because you're multiplying by something smaller in the numerator. So it's going to make that smaller. So it's going to be skinnier or thinner. And then lastly, oh boy, narrower for a 90% confidence interval than a 95. I'm not going to go back there and flip the page around a bunch, but basically same thing. The opposite applies from A, right? So we look at C, and we're just going to be using a smaller critical value, okay? And then thus, smaller critical value means a smaller margin of error, and then a narrower confidence interval. All right, when the population is normally distributed, population standard deviation sigma is unknown, and the sample size is n equal 15. Confidence interval for the population mean mu is based on which distribution? And this just goes to speak, do you know how to determine, so what you do is you scroll down here, or you're going to have this printed off. You're going to look at your sheet. And you're going to say, which one do we have to know sigma? Which one don't we have to know sigma? And you can look at population standard deviation known, question mark. Look down here at these confidence intervals, or I forget, maybe this question was the hypothesis test. Either way, for one where the population standard deviation is unknown, then you're going to have to use the T. When it's known, you'd use Z. And then binomial and Poisson are just nonsensical answers that were from module 4. Those are just distributions, but those are not ones that we use to do confidence intervals or hypothesis testing and whatnot. And number 5, in a manufacturing process, we are interested in measuring the average length of a certain type of bolt. Past data indicate that standard deviation is 0.25. How many bolts should be sampled in order to make us 95% confident that the sample mean bolt length is within 0.02 of the true mean bolt length? All right, so how many bolts? So that should be an indicator to how big is the sample size, which means you need to go and look for the sample size calculation formulas. And then, so how many bolts? So what is the sample size? Past data indicate that the standard deviation is 0.25. So this speaks to a population standard deviation, not a sample standard deviation. That's important. Okay, so basically right off the bat, then we know that this is going to be us trying to find sample size, which means it's an n equals formula. Okay, and we know that it's going to be z-based because we have a known standard deviation. So we would look all the way down here, and we find a z-based formula for that. N is equal to z alpha half sigma over margin of error, the whole thing squared. And then you always round up after that. That's that. So you guys run the calculation on your own, and you'll see that you get, I don't know, like 600 point something or other, and then that rounds up to 601. All right, so this is going to feel like I'm going through these quickly because I'm not going to walk through each step. So for that, I apologize. But what I am going to do is give you the logic of why we do what we do here. Okay, so it'll be up to you to practice to get there, but I'll guide you in the right direction in terms of, hey, this is why we picked this out. This is how we know this, that sort of thing. All right. And obviously, like I said, you can play this back, so I'm not worried about going too quickly because you can play it back. Cool. All right. A cell phone company makes its cell phones and delivers them directly to customers. The manager of the company knows from experience that the demand during lead time is normally distributed with a standard deviation of 60. Okay. He observes 30 lead times and records the demand during each period. With a sample mean of 265, construct the 99% confidence interval estimate of the mean demand during lead time. Calculate and interpret the confidence level. Interpret suggests, explain to me what this confidence interval means, or what it is and represents. Okay, so what is it asking you to do? It says construct a 99% confidence interval estimate. So construct a 99% confidence interval. So that's what we know we have to do. So don't use a hypothesis testing formula. Don't use a n equals formula. You're using a confidence interval formula. Okay. So we know that we're using one of 3 formulas that we have learned. We're using any of these module 7 formulas. We're using x bar plus or minus stuff, x bar plus or minus other stuff, and p hat plus or minus other stuff, right? So those are, and when I say stuff, I'm talking about the margin of error for that specific distribution. So the first one is a z-based, the second one is a t-based, and the third one is a z-based, but that's because we're talking about a population proportion. So the first thing we need to determine is, are we talking about a population proportion or are we talking about a mean? Okay, so we go back up here. Hopefully the spinning of the paper doesn't make you dizzy. And it looks like manager of the company knows from experience that the demand lead time is normally distributed with a standard deviation of 60. He observes lead times and records them, the sample mean. Okay, so now we know we're talking about a mean. All right, so we can automatically disregard the stuff from 7.4 and 7.5. It's not going to be about a population proportion. It's going to be about a mean. So it's either the stuff from 7.1 or the stuff from 7.2, the z-based or the t-based. Okay, how do we know what the difference between a z-based is and a t-based? Z-based we use when we have a known population standard deviation. T-based we use when we have an unknown population standard deviation, or we just have the sample standard deviation. So when we have a known, or when we have like a past data or anything that like suggests an industry standard for a standard deviation, that's when we're going to be using Z. So it says the manager of the company knows from experience that the demand during lead time is normally distributed with a standard deviation of 60. So this speaks to a population standard deviation. So we know that we're using the X bar plus or minus Z alpha half over sigma divided by N. Then from that point, we just have to find our 99% confidence interval formula, which involves us understanding the 99% confidence interval implies a type 1 error alpha of 0.01. And then this should be an exercise that you're familiar with, or maybe that you've memorized, of those four Z numbers that we associate with confidence intervals. 2.58 for the 99% confidence interval, 2.33 for a 98% confidence interval, 1.96 for a 95% confidence interval, or 1.65 for a 90% confidence interval. If you need to look those up, it's fine. You just look those up. We learned how to do that in a couple different modules. I think module 2 and then also module 5, where you just go into here and you would look for the alpha half probability. So what alpha half probability do we have? We have 0.005, okay, and we would look that up inside of our Z table, because we know we're working with Z because it's a Z-based confidence interval. So we look inside of this table and we would march down here. We just want to find the Z value that is the closest thing to 0.005, okay? So we just march down here, this first column. We're starting to see things that are close to 0.005. I see 0.0047. That is too small, and if we move right, it gets smaller, so we don't use that. We go to 0.0062, and then we move right, and we want to get something that's close to 0.005. It looks like it's somewhere between 0.0051 and 0.0049, and we want to leave the smaller error in the tail, so we'll just use the 2.58. If you use 2.57, I'm not going to mark anything terribly wrong or anything like that on the test. So we would have negative 2.58 or negative 2.57. That's where we get those numbers from. So if you haven't memorized those numbers, you can always look in the table and find those. Okay, and then it's just plug and chug with the formula. You have all the information in the problem. You have your sigma, you have your sample mean, you have your Z number that you just got, you have your sample size 30. You plug in these numbers and you get this confidence interval. And then the interpret is, and I just say this is the interval where we have 99% confidence that mu resides. Remember, when we run a confidence interval, the whole point of it is that we're taking sample information, okay, and we're trying to give some level of confidence where we think the population characteristic is, right? So the whole point is, hey, we took a sample, hey, we have this average. We want to have some reasonable idea where, like, the population average is, like where the truth is, you know, where it is for the overall distribution, where it is for the overall population. So that's what this is. It's saying we have 99% confidence that from 236.74 to 293.26, our mean, our population mean, is in there. That's that, okay? As opposed to just saying, oh, we took the sample mean and we think that the population mean is close to the sample mean. Yeah, that might be true, but we have no confidence attached to that. All right, so this next problem, a manager in a local bank is looking for some estimate of the average mean credit card debt for regional Northeast Ohio households. The manager found a representative sample of 50 U.S. households with credit card balance information. Using the sample, the manager obtained a sample mean X bar of 8325 and a sample standard deviation S equal 3150. Assume that credit card debt of Northeast Ohio is normally distributed. The manager is interested in a 95% confidence interval estimate on average mean credit card debt for Northeast Ohio. So this is very similar to the last problem. So first of all, it asks us for a confidence interval, so we know we're using a confidence interval formula. So we do the same process that we did in the last problem. It's either going to be one of three formulas from Module 7. So it's going to be x bar plus or minus the z alpha half stuff, x bar plus or minus the t alpha half stuff, or p hat plus or minus a bunch of p stuff. Okay, so that's that. All right, and so then the question becomes, is this z, t, well, is it x bar? Well, so we can see it is going to be x bar. X bar, the symbol, is given to us in the problem, so that's a very strong clue, but it also talks about sample mean. It also talks about averages. So this speaks to not being a proportion, this speaks to being an average. So from a test-taking perspective, I see that we've already covered a z, so I could assume that it's going to be a t. That's like if you had no idea what was going on and you just really needed to like take a wild guess, that would be a test-taking strategy that you'd use. But the next thing that we would use if we want to know the information is, why do we know that it's a t? Well, we know that it's a t because we don't have a population standard deviation. We don't have a sigma. We only have an s. That signifies that it's a t distribution to us. Okay. From there, it is very status quo. The only other thing that would be different from the last problem that I'll touch on is that finding the critical value for the t distribution is a little bit different than the z distribution. And in that you have to look at our t table and use degrees of freedom. So degrees of freedom is n minus 1, is the size of the sample minus 1, and the alpha half number. So alpha half is going to be 0.025 because we're working with a 95% confidence interval, and so then that's an alpha of 0.05 and an alpha half of 0.025, and then our degrees of freedom is n minus 1, so 49. So then we have to look in our t table to figure out what that is. So we first look at the t column of our alpha half, so however big the tail is, 0.025, and then we look down for 49. 49 is right here, 2.010, and then that's what we use in the problem. That's that. And then everything else is plug and chug. All right. 8, 9, 10. I'm not going to go over the extra credit, but I am going to go over these, and I have to be quick because I have to head off to school. The diameter of a precision ball bearing has a target value of 30. Target value, that should signify we're talking about a mean and talking about a population characteristic, so the mu. Suppose the bearing diameters have a normal distribution with a standard deviation of 0.085. All right, this signifies that we're talking about a sigma. Why does it signify that we're talking about a sigma? Because it says suppose. Suppose. We're making an assumption, right? It's not a calculation. It's not something that we have, you know, a small amount of hard data on. This is a suppose. So we're talking about a sigma. So already I can see that this is going to be a z-based test, whatever it is. When a shipment arrives, the consumer takes a sample of 49 from the shipment and measures their diameters to see if it meets the target value and finds the mean to be 30.6. So a sample size of 49, the sample has a mean of 30.6, so it's a sample mean, and then perform a hypothesis test at 5% alpha. So we have everything that we need. So we have our proposed mu. The only other question is what is the direction of all this? The direction of all this, does it meet the target value? And so we have to look in the context of the problem. The context of the problem is, what would it mean to be in error in this scenario? Well, it's a ball bearing. You want it to fit into whatever piece of machinery that it's going to be used in. And so overfitting or underfitting would probably be a bad thing. So you go equals, not equals in this scenario because you'd want to have error on both sides. So then step 2, we put our alpha in there. Step 3, we know it's z-based because we are given a sigma, right? Step 4, we establish our rejection regions. And our rejection region is similar to our confidence interval problem in that we split the alpha level that we have into the two tails. So 0.025 here, 0.025 here, and then we have to find whatever our z is for having 0.025 in a tail, which happens to be 1.96. Then we run our calculation, and we see where it lands in terms of rejecting. Okay, we run our calculation. We have some huge z-calc number, so we see that it's clearly going to be a reject because 49 is greater than 1.96, and then we have significant evidence to suggest that the population shipment, or the larger shipment, is going to be different than its target value. And then number 9, the national mean annual salary for bankers is $85,000 a year. A banker in the state of Ohio took a sample of 36, so we have an n equal 36, and found a sample mean to be 75.5, so sample mean, x bar, with a sample standard deviation of 7,200. So sample standard deviation, so it even tells you. So now we automatically know we're looking for a mean, and we have a sample standard deviation, which just auto means that this is going to be a t distribution. Okay. Assuming that the annual salaries is approximately normal, use a hypothesis test to determine if the mean annual banker salary in Ohio differs from the national average. Okay, so differs. Differs means that we're talking about an equals, not equal scenario. It doesn't say higher than, doesn't say less than, doesn't say more, anything greater than, doesn't say any of that. It says differs. So we run a hypothesis on equals, not equals. Okay? And then alpha is equal to 0.05. Because that's, I would have written that on the test. We know that we're using the t distribution because we don't have a population standard deviation. We only have an s that is given to us. So we find t similarly to what we did in the t-based confidence interval. We run our calculation with all of the information that we have using the formula from step 3. We obtain a number, and we look at that number in terms of the number that we had. Or in the rejection rule. And then we would find that significant evidence exists to suggest that Ohio salaries differ from the national average. All right, and lastly, this is the last one I'm going to cover, this extra credit I'm not going to cover. University of Akron students were asked which work schedule appealed most, predominantly night classes or predominantly day classes. U of A is trying to obtain statistical support that shows that more than 50% of students prefer classes before making any changes to upcoming semester offerings. Uh-oh. Hold on. Okay, good. Wow, I was running through this whole video and I thought maybe the video wasn't recording. That would have been a nightmare. Oh, man. Okay. U of A students were asked which work schedule appealed most, predominantly night classes or predominantly day classes. U of A is trying to obtain statistical support that shows that more than 50% of students prefer day classes before making any changes to the upcoming semester's offerings. A sample of 100 students showed 55 preferred the day classes. Conduct the appropriate hypothesis test at alpha level of 0.05. Okay, so here we're clearly talking about a proportion, right? We want to know that something is 50% more or 50% less, or whatever. We're already talking about a percentage. Anytime you see a percentage, you know that we're talking about a proportion. Okay. In this sort of status quo proportion is the thing that we want to know is it greater than 50%? So that's going to be like our proposed P, like our proposed proportion of interest. Okay. We have a sample size of n. We have a number of people that answered affirmatively in X, and then we can use that to create our sample proportion, so our X over N, 55 over 100. Okay? So then we know that we're using this set of formulas. Okay, where is it? Testing hypothesis about a population proportion. Z data is equal to P hat minus P naught all over P naught times 1 minus P naught over N, and the square root of that. All right. Okay, and so yeah, so we run our statistical test. We want to know, is it greater than 50%? So the thing that we have a suspicion of would be going in HA, right? And alpha is given to us, so 0.05. And so z is about a population proportion with this formula. Okay, so it's because it's z-based, we have a z-curve, and we have a rejection region on the right, because we always want to look at our HA, the directional there, to determine where the rejection region is. So it's on the right. And then we go ahead and we find the z-value that has 0.05 in the right-hand tail. Okay? And then we run our calculation based on our formula. So our x bar minus our p hat minus our p all over our p times 1 minus p over sample size square rooted. And that equals exactly 1. And where is 1 in terms of our rejection region? 1 is actually less than z crit. And so I say fail to reject because z-calc is not greater than z-crit. And then we don't have significant evidence to suggest that the student preferred day classes more so out of that sample of 100, even though it was slightly more than 100. Okay, guys, I got to get going. I got to run to school. But I hope this video helped. Sorry for talking so quickly, but I know that you can rewind it. As always, if you have questions, please, please, please email me questions while studying. And yeah, hopefully you all do well in this exam. These materials should be posted. Well, if you're watching this, they'll have already been posted. But alrighty, yeah, let me know if you have questions. Thanks so much. Bye-bye.